IMechE Railway Division South East event this evening, kindly hosted by the RSSB. My name's Chris Field, I'm Chair of the Division. Just before we start and go into our lecture, a couple of quick announcements after we do the housekeeping. The housekeeping is, if you need it, you found the toilets there out towards the lifts. If you need them, take your pass with you again. The fire drill, we're not expecting any fire drills. If there is a fire drill, please treat it as a real fire drill. Follow anyone who works for the RSSB, so Ben or Toby at the back, they're waving, or Barry there, to the fire exits, which are marked in the usual way with the green signs. Right, so with housekeeping done, a little bit about our next event, which is on the 15th of April, which is a full company Class 93 Stabber locomotives by Carl Watts. So that should be a really interesting event. Please do come along to that if you're available. That will follow our very brief again. So a little bit on that. We are a small team of volunteers in the community who put on these events, free for everyone to attend in the evenings. Hopefully you enjoy them. If you'd like to become involved at all, please do talk to myself or one of the other committee members. We'd love to hear from you. We'll have a brief AGM then, and this is notice of that AGM. Okay. That's it, I think, in terms of notices. So I shall hand over for our talk on low adhesion. I'm really interested to learn a little bit more about this. I am genuinely interested from other projects. One ABDO and things like that, which I'll talk to you about later. But really interesting, really topic. Gilbert Rowe has worked for and with London Underground for around 40 years. Too long. So very experienced. Very pleased to have you with us in the field. You've worked in braking, and sanding. Which come up soon. Thank you very much. All right.
Can you hear us from the online crew? Because the sound has become quite muffled since you started. Whether Gilbert can get as close as possible to the mic, that would help.
Don't really walk off with it.
How come?
Is that any better? Are you frozen, Malcolm, or is that just you? Right.
No, that's better.
Right. Okay. Good evening. All right, have you done your photo?
Just one more for good luck. Everyone keep facing forward. Thank you.
Okay. Good evening, and thank you for this opportunity to talk to you about automatic train operation in low adhesion conditions. Presentation is heavily based on my involvement with the adhesion management of work for 4 London Underground line upgrades. Those line upgrades have all successfully delivered ATO onto various parts of the Underground. The comments and suggestions are made with the great benefit of hindsight. There's no attempt here to be clever or snarky about anything that's been done. I should acknowledge that the presentation does utilise the outcome of various pieces of research which have been sponsored by the Adhesion Research Group and supported by RSSB. And finally, the views and opinions expressed are my own and should not be taken as indicative or representative of TfL's position currently or in the past. Okay? So, moving on. When you talk about open section performance, and particularly ATO, one of the key questions that comes up is what sets the performance limit, or what should set the performance limit? And hopefully over the next few slides, you'll get an idea about where I think that goes. Adhesion is, of course, refers to the level of friction between the top of the rail and the wheel treads. It's key to delivering traction and braking forces. It's key to delivering performance and stopping accuracy, and it's critical maintaining safety, minimising asset damage. All of that will be self-evident. Interesting to note that what people mean by low adhesion varies depending on who you're talking to and what problem they're challenging or tackling. There is potential for misunderstanding. Typical definitions, maybe it's when it's below a particular value, when it's within a particular range, or descriptively, it's when it won't support whatever demand you're placing on it. People will have a different view about that. I regret to say that I can't identify any any good consequences from low adhesion. Right? If you get wheel spin, you get increased journey time, you damage the railhead, you get wheel slide, you go past where you wanted to stop, you may end up stopping in a rather violent manner. And if you get wheel lock-up, it causes wheel flats, and not only does that damage both the train and the track, it causes an awful lot of stress to people living or working in the lives as well. Anyone who's been in a house above a train with bad flats will know exactly what I mean. These are the adhesion definitions that were developed some 25 years ago, when in the early days of the central adhesion management work. There are 7 definitions there. That may seem more than you might need, but it's necessary for the central line because you're braking at 0.75 meters per second squared, 8% G. You have a maximum deceleration of 1.4 meters per second squared. Therefore, the adhesion range needs to cover that scope. The term compromised is the one used to cover any condition of adhesion where it won't support the demand. Probably a statement of the obvious to say that the primary factor which affects any open section running is the adhesion variability, usually introduced by the weather. Very often, this is dealt with by the driving technique. The professional defensive driving are probably terms familiar to all of you. And the techniques used, effective though they are, all end up costing you performance. Operational point of view, the ideal is, of course, you can operate the same service all year round. It's not constrained to the low defensive driving scenario. Just touching for a moment on the braking issues which can occur under low adhesion. You can get extended braking distances, overruns, spads. Primary causes, well, clearly, if the adhesion over the stretch over the braking zone is below that which you need, you will get an extended braking distance. The adhesion required may be unduly elevated, either because of the way the brake system has been configured, as can say cross-blending applied to a particular bogie or wheel set, or because you're just asking for too much under the prevailing conditions. Your effective adhesion demand is too high. The interface and interaction between the dynamic and the friction brakes is an infamous example of where this can go wrong if you don't get that operating correctly. And you may, of course, have no adhesion improving capacity, or it may be inadequate or ineffective. So that means that anything you were relying on has suddenly disappeared. There are a number of possible mitigations. I feel that the simple statement here is to say you want some robust requirements, clearly defined, good technical spec, and a thorough design review and testing process. It, almost irrespective of what you apply that to, I think that principle holds. Now, if you're going to operate in ATO in the open section, things get a little bit more complicated. ATO is primarily installed with the intention of delivering an enhanced service. That means you're probably going to want to use higher motoring and braking rates than you do in manual. That implies you're going to need a higher level of adhesion. It also implies you're going to get an increased likelihood of wheel spin and wheel slide under the conditions when the adhesion is not quite there. That first of all needs acceptance at operational level. If you have people who don't like WSP activity on their train and sort of back away from it almost literally by winding the brake rate down, you're not going to deliver the enhanced performance. So that's a cultural problem. And if you're going to do this, it does require the rolling stock and ATO to respond, correct, and maintain on profile under those poor adhesion conditions. It should also be noted for those interested in this, even if the rolling stock can correct and compensate for adhesion variations, and the ATO can use that to keep it on profile, you may still have an issue if the ATP intervenes as a result of its intervention process or criteria. In case anyone's not totally aware of this, In ATO, a train will start braking at a calculated distance back from its intended stopping point. That distance will reflect the speed at which the train is going, the brake rate defined for that site, and any prevailing gradient and its effect. The inherent assumption is that the brake rate will be delivered. So the demand from the ATO is delivered by the train. Further assumption is the adhesion will then support that brake rate. A further, rather implicit assumption is that the ATO and rolling stock will quickly recover back onto profile if it does deviate off profile. Also, the ATP is not going to intervene and the train is brought to a stand at the right position under the control of the ATO. Those assumptions are not always valid, has to be met, has to be admitted. ATP, just to make it clear, its purpose is to ensure train safety. I'm sure everyone is aware of this. It stands for Augmented Train Protection. I'm sure everyone knows that. The risk does exist, however. The intervention process or the intervention criteria may result in the ATP intervening too soon, too often, or too frequently. Therefore, a sort of point of note, a point of question really, because I don't have the answers to this, but is there any merit in having some investigation, assessment, analysis of the ATP intervention criteria? Is there some need to develop some requirements for future applications to provide a core requirement? Should it be aligned with the rolling stock's ability to stop in low adhesion? Interesting points possibly for discussion. As a quick overview, these are the these are the open sections operating in ATO, pardon me. So you've got 4 London Underground lines, Central, Jubilee, Northern and SSR. And additionally on TfL, although not formally part of London Underground, you have DLR and Crossrail, which also operate ATO, at least in part. So what I'd like to do now is just spend a few slides talking about Central Line specifically, partly because it's the one that's been in service the longest, partly because it's the one I spent most of my time on. So there are key parameters which apply to any line, which can be derived and determined. This is much easier done in hindsight. Having done it, it's worth doing it for future ones. The emergency brake rate on 92 tube stock is supposed to be 1.4 meters per second squared under dry conditions. It's important that is achieved because that fundamentally underpins everything else you do. The maximum ATO service brake rate is also 1.4 meters per second squared, delivered through the electrodynamic brake primarily. The tunnel brake rate for ATO is 1.15 meters per second squared. And that means there's what I call a low adhesion headroom or profile correction headroom of 0.25 meters per second squared. That is sufficient to correct minor deviations such as may occur under dry rail conditions. So it's just tolerancing effectively. When you come outside, the open section brake rate is 0.75. That was defined by the need to deliver the upgrade timetable. That gives you a headroom of 0.65 meters per second squared, so virtually 100%. When the reduced brake rate was introduced in about 2010, that elevated the headroom to 0.85. And as a counterpoint to that, under severely degraded adhesion conditions, e.g. damp leaf film, even the use of 0.55 was not sufficient to prevent every overrun. Just shows how low the adhesion can get on Central Line. It's down to probably 0.04 of the leading wheel set of an 8-car train. Central Line trains the 1992 tube stock are 8 cars in length. They've got 100% wheel sets powered in. The ATO brake rates were determined on the basis of a targeted timetable. As far as I've been able to recall, there was no consideration whatsoever about adhesion issues in that decision. Early ATO testing in the mid-90s was severely hindered by the poor braking performance of the trains as they were delivered, particularly in the autumn leaf form. That was cured by fitting the trains with a per-axle WSP system, which not only restored the braking performance, but dealt with the horrendous level of wheel flattening that was being experienced. These trains are not fitted with train ball sanders. The idea of fitting sanders on a tube train is really quite a challenge. The idea of doing it retrospectively is mission impossible. When ATO was agreed to be implemented through the autumn 2001 was the first year, there was a daily requirement that said do not commence running an ATO until you've shown that it's fit to do so. And that catch-22 requirement is addressed by developing a condition assessment process, which looked at various parameters at about 3 o'clock in the morning, and from those determined whether or not we thought it was fit, and whether or not there was any immediate pre-start of traffic mitigation required. Having got into ATO, the requirement was to then operate in ATO at 0.75 metres per second squared for as much time as possible to maximise the service. And essentially, the philosophy for the central line application was to aim to operate at or just beyond the nominal adhesion demand so as to get the maximum benefit out of the system. At the end of the season, there was an extensive review, I think it's fair to say, which concluded effectively that went a lot better than anyone dared hoped. Possibly it went much better than many people dared were fearing, but it came out okay, and it resulted in the following changes for the future. Move to the 0.75 brake rate. We needed a second sandite capability to have one at each end of the line because we had one train originally, and we did not like the idea of running it through the central London tunnel. And the ATO risk reduction, which had been developed and was essentially an area based covering the East End only, had to be grossly expanded to cover both the East and West End of the lines, to be site specific and to be continually updated. This table here tries to show key mitigations which were in place both for autumn 2001 and autumn 2002 and onwards rather. So the big difference is there was 2001, it was East End only, significant vegetation management pre-season. There were a series of site inspections and reports introduced. They were done 3 times a day. And there was an emergency brake test train operated, which was a not-in passenger service 92 tube stop, which ran around the East End of the line about middle of the morning and sampled the adhesion by making a series of emergency brake stops. And from 2002 onwards, and I would stress these came in progressively over about the next decade, they didn't all suddenly appear overnight. We ended up with 2 mitigation trains, one at each end, 4 time-tabled paths per day per end, significant expansion of the leaf fall prediction and weather forecast in terms of resolution and frequency. The ATO risk prediction software, which some of you may know as the ACAT, was extensively developed, not only to provide primarily to provide enhanced and additional functionality. There was, of course, the need to address those issues which may come up during the previous season. Real-time WS capability was reported. The report was introduced from the leading cab of every train, and the rallied moisture sensors, which we acquired, were progressively developed to provide real-time reporting. Essentially, the performance over the years has been generally satisfactory. It's been relatively well received. The 0.75 has been maintained for the majority of each season and indeed over the year. Surprisingly, the 1960s Sandite train conversions have operated surprisingly reliably, albeit with a high level of maintenance between seasons. Should pay due tribute to the extensive mitigation efforts, mitigation train operation, maintenance, track inspections, vegetation management, leaf removal, etc., which were needed to help contain this problem. And there were, despite everything, a limited number of spads and overruns. Not unsurprisingly, I would suggest. But overall, it got a tick. This diagram here hopefully demonstrates what the adhesion in the vertical column, the conditions which might cause it. Across the bottom here, you've got the operational modes, which are emergency braking, maximum acceleration, service braking at 0.75, service braking at 0.55. 2 on the right, in this slightly disgusting orange colour, are projected values, which indicate what I think 92 would have achieved had it been possible to retrofit it with a modern variable rate sounding system, distributed lumber train. Oh, don't freeze now. What do I do for that? From central line, what can cause conclusions? Well, the first one is that open section ATO is possible, even on a line subject to a limited degree of lethal contamination. That's on 8-car trains with per axle WSP. Does not mean it would suit every train. They're not fitted with sanders, so there is potential for considerably better performance if you did have trains so equipped. It has required significant mitigation measures and resources during the autumn period. We've avoided having any serious incidents. Perhaps it's one thing we're all grateful for. Now, as I interpolated, I think if 92 had been fitted, it's just moving on from Central Line, the next two lines are the Jubilee and Northern Line. These lines were both fitted with the Thales Seltrack ATC system. The intention of the project was to have a variable brake rate system with 4 brake rates used in the open sections, switching between those as conditions required. That intention was badly torpedoed by the early testing in ATO, which demonstrated just how time-consuming and cumbersome increasing the brake rate under the ATC process was. Whether we bought the cheap version, I don't know, but certainly it made that approach completely unacceptable. It was changed to a single brake rate all year round. Jubilee and Northern Line trains currently operate at 0.5 and 0.3, effectively out in the open. Moving on to the S-Stock and SSR. The first point about this is S-Stock is the first fleet of LU trains to be fitted with sanders. Rationale for doing so, and this took quite a lot of discussions, was to assist in achieving the ATO brake rates. The key for that, the reason for that, was the ATC performance was the key to the targeted capacity improvement across the SSR network. The sanders were a late variation to contract. Unfortunately, it was by that time the train design was so well advanced, the sanders had to be squeezed in where they could be accommodated, rather than fitted where you might have wanted them to be. Certainly where I would have wanted them to be. And it was too early for variable rate sanding, which was not quite at the production stage. So that was a bit of an unfortunate mix-up. We ended up with quite a complex sanding algorithm to try and get the best out of what was, in politely terms, a bad job. And that's a bit unfair, but that's how it was referred to. And that required significant testing to develop and improve. Now, this was a significant point because it was decided to do this on the WSP evaluation rig up in Derby. And this was done in a series of phases, the first one of which was to develop that multi-vehicle whole train capability. Done that, we then did a whole suite of tests, brake rates over different adhesion profiles. I think it used every protocol. During the course of that, it was realised that what we could really do with is an ATO implement, which would automatically adjust the brake rate as the train on the simulator deviated off profile. That was developed, and that then led us into the final stage of testing, which was to redo all the testing under ATO control. The aim of that was to understand whether the higher brake rates in particular could be achieved around the central London sections and how much sand might be needed to support them. That was important because some of the trains, the S7s, have got quite a small sand hopper, so if it was going to leave a kilogram of stop, it was going to be less than a day's worth of braking. When S-Stop went into service, testing in 2017, passenger service in 2018, operation at the targeted brake rates proved extremely challenging, I think it's fair to say. The trains were frequently operated at lower brake rates and traction rates than intended, and the primary problem was the level of ATP emergency brake interventions. Now, these SSR brake rates, which are listed here, were considered high, but 0.9 is applicable to the so-called covered section of the circle line, the bits where you've got a road above you, and the others were considered achievable based on our experience with central line. If we did it there, we should be able to do it here from an adhesion perspective. Training these rates was critical to delivering the target timetable. As far as I'm aware, and I obviously haven't been involved for a number of years now, that has not yet been achieved in full. Thank you, Michael, for that. Right. So, what has been achieved in terms of open section low adhesion operation? This lists the lines, the targeted brake rate, and the currently implemented brake rate, what I perceive to be the performance limitation. Central line, I'm going to give a tick to because I was so heavily involved in it, so that must be perfect. It operates at 0.75 for most of the year, to be fair. It operates for a little bit of 0.55, and the fundamental performance limitation is the adhesion experience and the absence of any train-borne adhesion improving, such as sanding. Jubilee and Northern Line, as I tried to explain a little bit earlier, there were a combination of factors. When they operated at higher brake rates, they had a high level of ATP EB interventions. The brake rate change process precluded operating at those rates on a regular basis because you could never get back up. On a changeable day, you might have spent a quarter of an hour putting it back in and then be told to take it back out again. That went down like a lead balloon. And of course, those trains don't have any standards either. And for the SSR, where work is still in process, there are a range of brake rates targeted for different areas. The key problem, as far as I'm still aware, is the ATP emergency brake interventions, and that is constraining delivering the performance. This is not, in my opinion, an adhesion problem because it's not logical that it would be. This is about what's being managed or controlled. If you look at the lines from an ACC perspective, there are two systems effectively. Central Line enjoys the Siemens originally Westinghouse signal system that was first installed in Singapore, MTR, about 1984, I think it was. All the others have got a variant of the Thales Celltrack TBTC system. The latest one on SSR is renamed, but it's essentially, as far as I understand it, the same brand. The fact that they've all had problems with ATP interventions at a much higher level than you might expect from an adhesion perspective suggests to me there is scope to look at this and see what, if anything, can be done about it. But I think more importantly, perhaps, is there's an opportunity, perhaps, to develop and define some improved requirements covering what is really expected from ATO operation on compromised adhesion. This may take a bit of work and a bit of effort, but I think there's quite a lot of potential to squeeze out of this if you've got the requirements right in the first place. These are some ATC issues, if you like, and they're my views. So, I'm fully expecting to be shot by the signalling department. But on open sections, profile deviations are almost invariably the result of low adhesion. They're much more likely than, say, a failure mode. ATP intervention should be a very infrequent occurrence. Why would you expect to have a high level of ATP intervention? Doesn't make sense. Possible reasons why you might expect to get ATP intervention may be complete loss of the service brake demand, so the train doesn't actually start braking. Okay, but that would just take you through the speed curve, won't it? ATP speed measurement discrepancy, same thing. ATP braking curve exceeded. Essentially, they're all very similar. Now, there are undoubtedly others. I just can't think of them. Okay. It does highlight perhaps the importance of accurate speed information in this process, or perhaps a good way of processing the speed data that's provided. Sorry, did I miss something there? Yeah, if you get frequent interventions, you're highly unlikely to deliver the targeted performance. Therefore, there may be some merit in having a fresh look at this, perhaps just not just combined rolling stock and signaling approach to actually see what they are, why they work, and why they're defined that way. And I would have thought identifying and minimising constraints on service performance would be of importance to the operator because the whole thing is about delivering the service performance. This diagram here shows three speed distance curves drawn at three different brake rates. Get this thing to work. Here we go. Right, the green one is drawn at 0.6 meters per second squared, which is a typical ATO open section brake rate. The middle one is drawn at 0.75, which is a typical ATP brake rate at present. The open and the outer one, the brown one, is drawn at 1.2, which is a typical tunnel ATP brake rate. The yellow band indicates the area within which the adhesion improving can operate to avoid ATP intervention. And it's obvious that if you could go into the orange band, you could do a much better job at recovering it. So my question is, perhaps this is where we ought to look. Perhaps we should make use on trains equipped with a distributed effective proven adhesion improving system. Why not utilise it out in the open and give yourself more scope to recover? You would clearly need to have a well-proven system, and you need to make sure it was kept well maintained and operational. That might be something which would cause some debate. And this is the same diagram, but with a typical low adhesion profile added to it, shown by the dotted line. Deviates off the profile, and then as the adhesion improving kicks in, it recovers back. The more effective and better the adhesion improving, the faster that happens. So the other slide I'm going to flag up about ATC is about accurate speed measurement. Now, I'm going to say I do not claim this is particularly original as a slide or an issue. Accurate speed measurement on ATO has probably been a subject almost as long as ATO has been around. So classic arrangement is ATP tachos on 2 axles. Ideally, you try and fit them to unpowered and unbraked wheel sets. That may not always be possible, depending on the train configuration or the length of the train. So can you supplement? Now, there's an awful lot of speed data on most modern rolling stock. They've virtually got speed sensors, at least one on every single wheel set. So I would have thought there would be some way of utilising that data to assist and support the ATC. There will doubtless be objections and issues, but in principle, I think this is worth revisiting. It's a long time since I think there was a really robust discussion about this. Ideally, I would suggest you want speed output independent of wheel set rotation, get rid of the whole problem on the slip side. Again, not particularly new. Doppler radar has been around for, I don't know, 25, 30 years probably. But I would draw attention to a trial that, I'm sorry, Ben, I'm going to advertise ARG again, which was initiated by ARG called Dependable Speed Measurement. That used an inertial accelerometer part of it. That did produce a very accurate speed signal, even under low adhesion conditions. Whilst that was done with the idea of using the WSP, there may be more benefit, even more benefit, if you could use it with the ATC. Now, the problem I think that comes into this is who decides how you're going to do the speed measurement? What level of accuracy you're doing? Is it left with the ATC supplier? Does the railway need to have some really clear requirements about what it expects from the speed measurement? I think there is again scope to discuss who defines what. Rolling stock's point of view, low adhesion braking has come on significantly over the last 2.5 decades, I guess. Probably most primarily from about 2000, 2015. But from the mainline's point of view, they moved from single fixed rate sanders on the train to multiple sanders, variable rate sanding, dual variable rate sanding systems. And it has dramatically improved the low adhesion braking capability. So the question then becomes, are you going to utilise that? Or are you just going to think, that's a good bit of research, we'll put that in the bank and look after it? Well, there are a number of potential issues that a number of people have raised at various times over the last few years. And it essentially boils down to how much confidence have you got this will deliver when you require it to? It's a perfectly reasonable question. There are a number of issues which relate to the rolling stock: sanding system design, the sanding component design, the sander system monitoring, self-monitoring, the detection of faults and problems. Blocked sander nozzle will be an issue to everyone for very obvious reasons. Sander maintenance and refilling, just how much resource and logistics are required to refill a fleet of trains overnight? And from the track engineer's perspective, there may be an issue about more sand means more sand in their points and crossings. And therefore, is there a need to think about automatic inhibiting of service brake sanding on the approach to P&Cs? Is that something that needs to be added into the discussion? I'm not going to claim to offer any answers to this. I'm just going to pose this question. I'm going to leave the next generation to take this away and deal with it. Assume for the next few slides, if you wouldn't mind, that the business requires this to be exploited. Right, so once the capability exploited, it wants the maximum performance. That's where these slides go. So you could use that and say, we're going to enable enhanced braking. Let's call it step 2 to keep this discussion simple, all year round, even on degraded adhesion. That might result in some quite interesting or exciting or terrifying stops on degraded adhesion, but it is possible now. The alternative approach is you can say, use that for 95, 98% of the year, but retain the option of going back to a lower rate of braking under severely degraded conditions. That, of course, would require you to identify those conditions in advance. And this has got the advantage, in my opinion, of being more pragmatic, more prudent, enabling a more progressive and incremental approach. So there are a number of advantages if you could do it. To answer my own question from earlier in the presentation, I think this should be the rolling stock low adhesion capability that limits what you do with the train. It would be on a manually driven train. Why should it be any different for an ATC train? Sorry, oops. So, implications for future ATC applications. From an adhesion perspective, it is possible to operate at adhesion levels of around 0.06 to 0.09, okay? But it does require the characteristics and capabilities from both the rolling stock and the ATC, depending what they are or wrong, will severely impact on what you can achieve. So let's assume you're going to operate at what I'll call a mid-range break rate, 0.6, 0.8 meters per second squared, around the central line figure. You want to achieve that over severely degrading adhesion. So clearly the rolling stock has to be able to achieve that stopping, and that dictates various characteristics, like you need enough headroom between the nominal and the maximum service break rate. You've got to have the adhesion improving, doing its stuff, and improve doing it. But you need the ATC to allow the ATO and rolling stock to recover onto a profile whilst experiencing sustained WSP down the train with minimal risk of the ATP intervening because its ATP intervention criteria say it needs to. So, how might you exploit this? Well, my opinion is that this may involve the development of some more detailed, more stringent requirements covering various aspects of ATO under compromised adhesion. For example, you might define the break rates and adhesion ranges over which you require the rolling stock to operate without overrunning, and the ATO to operate without ATP intervention. You probably want to include those in both specifications to avoid anything falling down between the cracks. And you certainly want to put some requirements about how you want that tested and demonstrated to show compliance before you pay for it. Certainly before you let it loose on the road. These are things which I think you would need if you were going to try and do this. You'd need the adhesion improving system, you'd probably take that for granted by now. Comprehensively tested for speed, stopping distance performance, consistently effective over the operational speed range, and able to raise the adhesion level from horribly low to tolerably high. The brake system has got to provide the headroom, and the ATC has to allow recovery onto profile before intervention, and I think it should be consistent with the rolling stock low adhesion braking capability. That may, of course, mean you end up, the suggestion may result in different ATP intervention triggers for different lines. That may have its own issues, but it may be something that is at least worth considering. And combined rolling stock ATC testing to demonstrate compliance. The question will at some point come up, probably very much earlier in the process you want, about is all this worthwhile? Is it cost effective? I don't know, is the honest answer to you. It may be application specific. It certainly is possible to deliver this enhanced braking. It potentially offers benefits if they can be extracted in reality. It obviously requires additional equipment that will have some maintenance implications. That may present a conflict with people's desire to reduce operating and maintenance costs. And it's entirely possible that the driving style of WSP and regular adhesion improving operation is not going to be well received at all levels. So, some conclusions. Sorry, did I jump over to? Yes. It is possible to run in ATO on the open sections, and it is possible to do it even in lethal vulnerable areas. The achieved performance will be constrained by various factors, such as shown here. If you're going to go for the high performance option, I think it's critical that there are some really clear, detailed requirements about what you expect, not only on dry, which is the easy bit, but under compromised adhesion conditions, which is the bit which presents more of a challenge. The rolling stock needs to be fitted with our distributed improvement adhesion improving system. I deliberately avoided using the term AI for adhesion improving because I think of the confusion that might cause. And the ATC needs to be designed to both operate over that range of adhesion and to have been tested accordingly. So, I would advocate, from my experience, you seek early evidence of what you're able to get out of the ATC and the rolling stock. And even if that needs to do it with a not totally representative combination of systems, getting early data is invaluable. It gives you a chance to have things modified before it's too late. The rolling stock certainly needs to be comprehensively tested with the ATO, and I can only say from my experience, simulation testing approach to be used on S-Log was highly effective and a good deal more time and resource efficient than track testing. If you want to go to extremes, you could even consider some sort of pre-contract testing of the ATC and or the rolling stock to demonstrate how well or how badly it might perform over degraded adhesion conditions. It depends how important achieving the service performance you've targeted really is. So, safety performance from an ATC system, you need to think about, I think you need to review not only ATP intervention criteria, but the process that is used to determine what the ATP speed is. And the service performance, I think, should be constrained by the low adhesion braking capability of the train. If that's not there, everything else becomes a bit irrelevant, because all you do is drop the emergency brake. And on bad adhesion, that doesn't necessarily help. And I would have thought identifying service performance constraints should be a key focus for the railway authority or the operator, however you want to describe them. And that leads to the question, is the level of railway authority involvement with this process sufficient, or does it need to be enhanced? Does the railway authority have the capability to provide that sort of insight and supervision? Future possibilities. Right, these ideas, and they are just ideas, are intended to be applicable to both manual-driven and ATC lines. And if this suggested operational objective summarises what people really want, then if you're going for the enhanced performance, you clearly need the rolling stock to provide a consistent, reliable, low adhesion braking capability. Fundamental. Is that adequate for all circumstances? Possibly not. We've seen the reservations that have been identified about that. So if it's not, what about the idea of supplementing this with knowledge of the adhesion available for the next stop? Now that sounds like an interesting concept, doesn't it? This would mean some form of adhesion measurement capability would be required, proven. But in principle, you could use that, or could you use that to determine the adhesion level for the next stop? If you could you then provide an output to the driver or the ATO in advance of when it needs to start braking to say you want to use the lower or higher brake step? So if you were going to go down that route, you need something that can measure, process, collate and communicate adhesion data between trains. You might do a rolling assessment over the required braking distance, which I guess could be anything from 0.5 kilometre to 5 kilometres perhaps. The purpose would be to identify when conditions are fit for higher rate braking. And my suggestion is, why not base that on the adhesion measurements from the preceding train? You use the lower rate of braking as the default, the higher rate of braking only when identified that conditions are up for it. You restrict this almost certainly to things with a really good adhesion improving system, such as DVRS. And the primary purpose will be to identify the rare but ultra low adhesion conditions which have been responsible for so much grief, so much trauma, and a number of incidents and unfortunately accidents on the railway. So you could indicate this when, say, the adhesions are 0.05, possibly. Whatever value, you can plug in a value as appropriate to that rolling stock. And if it's below that, you indicate the lower rate of braking, and you could even preemptively trigger the adhesion improvement, i.e. start braking. That is possible in principle. So if this idea has got any interest or advocates or supporters or whatever, you might end up with a concept system that looks something like this. And I stress there is no substance behind this. This is just a concept diagram that I put together. But you have trains fitted with the adhesion measuring capability. Ideally, you would also be able to detect railhead contamination, which may not be giving you low adhesion if it's not done. The data from the train ahead is then used to inform the following train. You supplement that with data from that following train, and from the combination of those, you generate a rolling adhesion available for the next stop. And if that's above a defined threshold, then you could trigger the indication for the higher rate of braking. This scheme may have too many issues, agreed. It may be too big a challenge for the industry to take on, possibly. The benefits are unlikely to be realised for quite a while because it's quite a lot to do. done before you could roll it out. But it does offer this option about being able to retain the lower rate of braking for the exceptional circumstances. Potentially, that might be quite worthwhile. There is, of course, a further variant of that, which does away with the data transfer. You just say, don't bother with that. We'll just use the adhesion measurement and we'll use it effectively to turn on the adhesion improving preemptively. Is that seen as worthwhile? That's an interesting question. It does place greater reliance than the previous one on the adhesion improving system, but it does not require any data transfer. It's still questionable about whether or not the benefits could be realised fast enough, I think. And finally, bring this to a close. How much is extra performance really worth? There are a lot of figures bandied around about how much extra value you can get from it. Does it ever materialise, really? How much does it really cost to sustain this into the future? What is involved here? Against the background of continual reductions in maintenance and operating costs. There seems little value to me in fitting modern variable rate sanding systems on a distributed basis if you're not going to utilise the capability. What are you going to do? Just carry the weight around. If it's not used, it will degrade, and then when you come to use it, it won't work. Not that that's something we're ever familiar with, that doesn't happen. For ATC lines, I can only say the ATP intervention process and criteria may be a constraint, and I would advocate it's reviewed accordingly to make sure it isn't. And this, of course, is a multifaceted problem. This is not new. Everyone knows this. It cuts across all the assets, all the disciplines, all the departments, cross-asset, cross-discipline. If there's any real intention to make a significant change, it's going to need some really good leadership, really strong leadership, I think, some very clear direction, probably some very sustained commitment. I'm not going to comment on whether I think that's achievable or not. I'm just going to bring the presentation to an end at this point, and thank you for your attention.
You have to say some questions.
Yep, whether I can answer them or not is another question, but I'll try.
Thank you very much.
Gilbert, thank you for the presentation. It was very interesting. The two-part question, your concept at the end for adhesion measurement, can you explain how that adhesion measurement would be done? And second part, related to our conversation earlier, as you know, KB are doing that on a trial and have the capability from our brake systems. And would that fit with this concept?
One of the other adhesion research group commissioned initiatives was the development of an adhesion measurement capability, and that was undertaken by the University of Sheffield 3-4 years ago, I think it was now. And there is a very interesting report that's written, is available, I believe. I know it's university available this event. It is, yeah. Which demonstrated that it was possible, or it is the first stage of demonstrating a production adhesion measurement capability. Essentially, it was proof of concept, I think.
Sorry, that contacts the railhead?
No, it was via a camera system, if I remember rightly. It was fitted on the front of the train.
Okay, so not actual adhesion calculation?
No, it's not a calculation. This measures it.
So,
this measures it from the imagery.
No, that's fine. It's fine. But that isn't actually the adhesion achieved. It's a image of what
it's the adhesion as measured from it. So the first, if you're going to take this any further, one of the things you'd have to do is get some correlation between the adhesion as measured by that facility and the WSP activity experienced at the same time. Because then you could do something to correlate what the measurement says and what the WSP says, which is actually what you're interested in.
Okay, maybe a topic for another. I don't think cameras can't measure invisible adhesion, right?
No, they take the image from the track and they use that to identify the adhesion value which it represents. That was the essential guts of the work that was done.
Okay.
I think it's fair to say that is the first stage of this. This is why I stress this is a concept. There are a lot of things that would have to be done to move this from idealism to reality. Okay.
Right.
I don't even know this is possible, to be honest with you. I don't know how much more, what next you would do with the adhesion measurement capability. I think there were a couple of trials going to be done on, I think, some mitigation vehicles about using it just to see what results they got. I don't know whether they actually got any results. But clearly, if you're going to do this, you would have to do a lot more work on the adhesion measuring prototype, let's call it. You'd have to see how consistent it was, how it correlated with the WSP, what was necessary to get a production version. I'm not even sure with the what maintenance is needed to make sure the camera has a clear view of the railhead. If it needs cleaning every 24 hours, that's going to make it a complete no-no. So yeah, this is, as I say, just an idea which is dependent on some stuff that is not really proven yet. I think it's fair to say.
So a direct measurement from the railhead would supersede that.
Depends what you mean by direct measurement from the rail.
Well, so under WSP, the dump valve activates, and a modern braking system has the algorithm to do that, right? As you know.
Absolutely. And
So from that, you get the adhesion,
you can
actual
calculate,
adhesion.
you can calculate the adhesion.
Calculated. It can be calculated on the edge or in the cloud. So you effectively have the adhesion that was, rather than a visual interpretation of it.
You have an adhesion which is subject to the tolerance of the brake pad or brake block friction measurement. You can't actually be sure what that is. So, you know, when you say you calculate the adhesion, you calculate it based on brake pressure and an assumed friction value.
Okay, and that's better than a visual or worse than a visual.
I think there are pros and cons. Shall I just leave it like that?
All right.
And I think you might end up combining the two of them.
Yep.
Yeah. And that would be a useful thing to do because it would help validate each of them. You know, you could bring the two to a combined output. So yes, I'm not saying this is the way to go. I'm saying this is a possible way to go if anyone thinks
Basically, we need to measure adhesion. Yeah.
Right, sorry, was there another question there?
But there was, but we won't get bogged down because there'll be other questions.
Thank you.
So great presentation, Gilbert. Thank you. I think possible concept system's good, but I think it needs with it the thing you alluded to earlier, which is being able to have the headroom in the system.
Absolutely.
To control the train without the ATP dropping. So that's a key one. And I think a lot of this alludes to what the train can do. In your opinion, what are the other big factors in controlling the adhesion level, giving the train the best chance on the railhead?
It depends how you want to approach this. I mean, there are some very conventional, very traditional ways of trying to minimise the risk of low adhesion. Classics, vegetation management, classic mitigation trains. Both of those, of course, require significant resource and budget to implement. However, if you're going to operate through lethal areas, it's really difficult to see how you do it unless you maintain those, particularly the mitigation train operation. The more you cut back on the vegetation, sorry, no pun intended, the more you reduce the vegetation management, then the bigger the need to have effective mitigation measures, I would suggest. But fundamentally, if you've got an appropriate base level, I'm tempted to describe what I think that is, because it depends on the railway, it depends on the specifics. But if you've got that and you've got the train equipped with a defined and tested level of adhesion improvement, then I would suggest you want to exploit that. Otherwise, why have you fitted it? You're not going to fit it for the very rare event in the case that you have something. You know, I don't really want to allude to Salisbury. Salisbury is the classic example where everything went wrong, right? Pretty well, or many things went wrong at the same time. And they're fortunately very rare. So and I think, as we've discussed many times, developing a business case to fit some purely safety reasons is virtually impossible. You have to have some really horrific event to, I think, justify that. So therefore, if you're going to do this, it has to be used in service, it seems to me. Otherwise, where is the justification? Does that answer your question?
Yeah,
Thank you. Graham.
You mentioned earlier that ATP intervention is a big problem on the existing SSR stock, I think it was. I think it's also a problem on Northern Jubilee line.
It is. It was originally, particularly the higher brake rates.
So I've heard over the years many discussions on how to fine tune the safe braking model and all these other things. But when an ATP intervenes, it usually means the train has reached, let's call it the ATP safety curve, and the emergency brakes are applied. I think what you're proposing, I just wanted to get clarification on this, is that when it approaches that safety curve, then the train takes alternative actions to try and stop it breaching that safety curve. Or are you saying that once it's breached it, we can take alternative but safe actions to bring it back under the curve, but not necessarily put flaps on the wheels or whatever? Can you just sort of describe?
Sorry, right, okay. What I'm saying is ATP intervention is essentially the last resort.
Yeah.
It should not be the first response. And all too often at the moment on SSR, it seems to be the first response. It kicks in before the WSP has a chance to operate. Well, that doesn't make sense. So you want to do it so that the WSP and the sanding system work first in response to the onset slide. That means the ATP intervention process or criteria must need to be set so they don't cut in too quickly.
That's what I was alluding to.
Once you've got that point, you get the low adhesion braking capability invoked, and then it needs sufficient headroom between the ATO and the ATP curves to be effective, because it doesn't happen instantaneously. And this may be another misunderstanding amongst some of our colleagues. You cannot correct instantaneously. You've got to get the sand out. If it's sanding, it's then got to take effect. So you're probably talking potentially about 10-second or more time between starting it and actually seeing a really beneficial effect. And that's why I've shown that curve sort of deviating off quite a way before it starts to come back in. Now, the better the adhesion improving, the faster that happens. So yeah, all I'm trying to say is that I think at the moment you may have an ATC system that is unduly constraining the service performance, is preventing the rolling stock exploiting its low adhesion braking capability, and therefore you're losing a lot of service performance. And I know there's been a lot of work done tweaking bits of the rolling stock software on those projects, I believe. I don't believe that there's been a really detailed review from the ATC side. And I understand why that may be the case, because the issues associated with changing the ATP doesn't mean it's not overdue.
Sorry, that's what I was alluding to. I think there's more that could be done on the ATP side.
Absolutely.
And the train to stop it getting to a point where the emergency brake has to be applied.
So say, providing you've got confidence in the train's low adhesion braking capability, why not make use of it for the benefit of the performance? But it's not without its issues.
Sorry, can I just, I'm going to just ask a follow-up one. There's a snake in there, apologies. So on that, interesting, all of those different elements that you showed in one of your latest slides, how integrated does the train system need to be? Does it need to be 100% integrated, or can you live with a WSP system, a sanding system, and other systems on other trains that report back being disparate systems that interface?
As far as each train is concerned, it's very important. The system, WSP system, and sanding systems are appropriately integrated and interconnected, because they need to all operate together. In terms of the communication with other trains, that really depends on how you want to deliver performance. If anyone thinks that the idea of communicating effectively, that's clearly one option, I'm not really advocating that as a solution, then all of the issues associated with that would need to be addressed. You'd need to make sure the data went to the right train. You'd need to make sure it was received by the right train. There'd be a whole series of issues just with the comm system, I suspect. That's why it's much easier to just do it on the basis of individual trains. Ultimately, it comes back to what the requirement from the business is. How serious is it about really pushing the performance barrier? And I have to say, personally, I'm not convinced it is, when it comes to the crunch, really serious about it. I think it's, if there was a simple way of doing it, it would have been done. In fact, there isn't. It suggests it's going to be a challenge to get anyone to take this forward. But I mean, this will be for others to deal with, because this is my last sponsor.
Great. Thank you. Let's go to Malcolm and then we'll come to you.
Hello, Gilbert. Congratulations on the excellent talk. I think you've underplayed the role you involved on the central line. You were Mr. Central Line Adhesion, and you had to work so hard to convince everybody else that it was the right thing to do. And with the benefit of hindsight, it was absolutely the right thing to do. So congratulations on that. I equally think that all you've said about the integration between the various bits of train system and the ATP is absolutely vital. I think the challenge is that rolling stock people seem to be quite flexible, and dare I say it, the signalling engineers aren't. Possibly not helped by the fact that the cell track system was developed for railways where the braking system was largely independent of adhesion. I do think that there's some more headroom could be put on the braking curve. The question is, of course, is how much? You know, if it's currently 3.5 kilometres, would 4.5 kilometres or 5.5 kilometres an hour be enough to give you the time for the WSP and the Sanders to gather themselves and do their work? That's the question I can't answer because I don't have enough knowledge. And I was fascinating listening to you and Graham debating it just now. But I think that's probably the key to making it all work in the future. Over to you.
Yeah, thank you, Malcolm. Very generous words, thank you. But in terms of that, in terms of what you're suggesting, I think let me think of the best way of describing this. The capability of the train is obviously key to this. The train doesn't stop on low adhesion. Anything you try to do in terms of control isn't going to work very well. So therefore, the first thing is this low adhesion braking capability. Now, none of our existing trains have got what I would call a really satisfactory low adhesion braking capability. Central, Jubilee and Northern Line have just got the WSP, but limited improvement that can make. SDOC has a first generation sanding system, if you like, which is either distributed the way we know the term now, or variable rate. So its capability is quite badly constrained. Therefore, I'm not sure whether there's any scope with SDOC, the SSR, to get a bit more out of it. I think there is, because you're not operating at target ATO brake rates. So if you've got it up to that, then you might have a better idea. I do think that there is scope to work with our ATC colleagues, and I'm not going to comment on your judgment about respective personalities of rolling stock and civil engineers. I'll say I agree with you. But you could, in principle, set up an appropriate set of off-track, or effectively simulation tests to see how that would perform. What changes you could make in a off-train environment? How much assessment you could get out of it? Ideally, you probably want, like the ATC supplier, to have a simulator which does this for you anyway. You might think they need it. And I agree with you. If I don't want to make it too personal about one system, but if the Tunnis cell track system was, as you say, developed for trains with a fundamentally different braking system, which was not so reliant on adhesion, then the criteria they devised may not be appropriate to the use that that TfL have put them to. So I fundamentally, I think I agree with you, but how that gets taken forward is another question altogether.
I'll take comfort from the fact you agreed with me for once, Gilbert.
In fact, you will recall that I actually used your quote on the Central Line 1 about operate at or just beyond the nominal adhesion level. Those were your words to me 25 years ago.
Oh God, I can't remember ever saying that. But
anyway, sorry, does that answer your question? I'll try to.
Very much so. Thank you, Gilbert.
Another question.
Yeah. Hi, Gilbert. I've had the pleasure of working with Dave Orme for the last 4 years.
Right.
And I mentioned I was going to see the talk today, and he said, put your hand up and ask you a question and say hello. So
he didn't bother to come himself.
he wasn't aware, but he said he wants to send his regards and that you're doing well. But I just wanted to say, so I've been working on DLR the last few years. We're now retrofitting Sanders to our new vehicles. So I wanted to understand a bit more around what you were saying with regards to the challenges around retrofitting Sanders and also around the whisper rig tests and how you'd relate that to testing that you do on site, because that's the challenges we've got to do in the next couple of months. That's what the programme. That's what the programme.
Yeah, sorry, I'm not going to be here all night. But
Yeah.
in essence, it comes back to what DLR as an organisation wants to achieve before they fit this stuff. The point about fitting sanding is to make it to deliver an improved performance under low heat. I would suggest, therefore, you need to understand what that performance is going to be before you specify the sanders. Right. Now, I don't know whether you've specified the sanders or contracted the sanders yet, but I would suggest that it's worth doing some testing before that contract is finalised. Now, if you choose to go down the simulation route, like I did on SDOC for TFL, then there is a fair amount of setup to do with DVUSG and the facility in Derby, which mostly revolves around the sander configuration and its potential capability. That may need some track testing to what they call characterise the sander in terms of the sanding rates, the sand density, and the change to the wheel set behaviour. And what you can then do on the whisper rig is try and replicate that at very brake pressures so that you get the same wheel set behaviour. If you get to that point, you can then effectively make up the model, adapt the model train to have the sanders on the appropriate vehicles. Then you can run that train over a suite of adhesion profiles to see what performance is practical. And I can only say from my experience, it proves worthwhile, but it's not a 5-minute job. By no means is it 5 minutes. And of course, you've got this complementary issue about the maintenance facilities in the depot, the refilling, the appropriate care and protection of the sand itself, the treating of it as effectively now almost part of a safety system.
And the reliance element that you mentioned as well in your slides, which I think is very relevant to what we're doing.
Yeah, I mean, this is where the more distributed the sand system is, greater resilience it's got, because the failure of one shouldn't result in the failure of the others. That is badly compromised, of course, if you've got damp sand in every single hopper. So there are all sorts of issues which need to be thought about and addressed. And I would almost say almost the biggest challenge occasionally is the cultural one about, you put sand in the depot, people will think, well, it doesn't matter, just leave it outside, get wet. You may have the wildlife, the maintenance staff urinating in it. Now, all of these things are very real problems. They sound disgusting, but they all happen, and that's the problem with it. So yeah, good luck. I mean,
Yeah.
Toby.
Thank you.
I think I saw in one of your earlier slides, Gilbert, you said there was collection of leaves. Is that,
Leaf collection.
leaf collection, yeah.
Sorry, let's go back. This was on Central Line, wasn't it?
Yeah.
There's the key mitigations, wasn't it? There we go. That one there, I think. Is it that one?
Yeah, I think it's
On the
left-hand side.
I just wondered if that was just was that
yeah, leaf collection.
something that was done
One of the
manually?
things that was discussed when all this was set up in 2001, nobody was quite sure how far we needed to go the first time round. So some of the early work identified what support we might need from the track and vegetation teams. Key part of that was the vegetation management, the sort of conventional stuff, if you like. But along the central line, there is quite a lot of fallen leaf litter which collects in the cesses or in the tracks and the points and crossings. And it was felt that the regular removal of that would be worthwhile. Now, the only way that they were able to do that at that time was to do it in the engineering hours. And in fact, you literally go along and pick up hundreds of thousands of leaves. And I think, if I remember rightly, there was something like, I'm trying to remember the figure, was it 300,000 leaves collected over the course of a season? I think it was estimated by counting the number of bags. It may have been more than that. So yes, it's how much difference it made is almost impossible to gauge, because you just seem to be fighting an everlasting army of leaves falling on your track. But yeah, it must have helped. And I say that because there was one year, and I can't remember which one it was, where we had a period of about 10 days when we had a speed rush on the east end of the central line. and it was limited to, I think it was 30 miles an hour or 30 kph. Doesn't matter. Then one afternoon, without telling anyone, that speed limit got lifted, and the trains, instead of running past at trundle speed, suddenly started hurtling past. There was this immense collection of leaves that built up in the cesses, and it was just all thrown into the air. And I think we had 3 overruns in half an hour as a result. And that was just something which nobody would have thought about, I don't think. You know, nobody bothered to communicate that they were going to take the speed restriction off. Understandably, why should they? Their track. They can do that. There you go. And it's that sort of thing which is almost impossible to guard against. Except the only thing you can do is have adhesion improving on the train to cope with the unexpected.
Wasn't leaf collection data also used to help supplement the ACAT to identify when the leaves were falling and when they were?
That wasn't the leaf collection data, Graham. The leaf fall predictions that we got from originally ADAS and then the Met Office provide a lot of data on that. And yes, there was extensive use made of that data within the ACAT logic. And there are people here who have suffered through the implementation of that logic.
Good. One more
Right,
question.
one more question on the emergency brake test train. Could you be
Emergency brake
interested,
test
Gilbert,
train.
on how it works?
Right.
Predate that date.
The emergency brake test train was put in place because we wanted to gain some understanding of how often we might experience bad adhesion. So we arranged for a 92 tube stop, which was not required for passenger service, one of the Central Line trains, to take a timetabled path around the east end of the Central Line. We set up a series of places where it would make an emergency brake stop. And we put in place some line side track markers, which I think went up to something like 200 metres, 250 metres. And so the test crews who drove these trains were instructed that providing the signals ahead were green, so that we weren't doing this at a point where we might conflict with another train movement, they would apply the emergency brake at a defined speed, and they would record which marker they came to rest by. That data was then passed back to the people who were monitoring this whole process. I'm happy to say in 2001, I had a very enthusiastic young graduate working with me who did all this, so that took that off my. And essentially, we just looked for evidence of poor adhesion. And I think we kept that up for 2 or 3 years, at the end of which those trains then were needed to support the enhanced timetable. And we hadn't experienced any grossly degraded adhesion on those stops. Now, that's just a matter of luck about when you hit the adhesion. Maybe the morning was the wrong time to do it. It was the only time you could get the timetable path. So, and if you did it in the dark, you couldn't see the markers. So, I mean, that was a bit of a non-show. No one was prepared to put lighting in to see them in the dark. Does that answer your question?
That's great, Gilbert. Thank you.
Okay, no problem.
Good. Well, I'm sure there'll be plenty more questions afterwards. We'll leave it there. That was a really, really interesting talk. And I think we don't often get talks that get some of the technical detail, but also provide such a high-level overview of the strategy and approach to a topic as well. So yeah, fascinating and challenging, thought-provoking as well. Thank you very much. You're welcome. We